So let's finish up. Let's complete section 2.5 on completeness. Recall, a norm-linear space is complete if Cauchy sequences converge. So to deal with completeness, we need some equipment to determine when Cauchy sequences converge. And the next result is useful in establishing the convergence of a Cauchy sequence. Lemma 2.13 states, suppose that X is a subspace of the space of all functions from set S to field F. We denoted this as f of S in the past. And that subspace X has this norm on it and satisfies the conditions that the closed unit ball, B bar of 1, is closed under pointwise limits. We need to elaborate on what that is. They're actually sneaking a new definition in at this stage. But first, the fields, of course, the fields we're interested in are the real numbers or the complex numbers. Closed unit ball, we use this notation in passing, maybe in the past. This is the closed unit ball centered at 0 in the normed linear space. So they had this little shorthand notation for that, but ball of radius 1 and center the 0 vector. Okay, so we're requiring that this closed unit ball be, quote unquote, closed under pointwise limits, and here's what they mean by that. That is, if Cauchy sequence f sub n is a subset of the closed unit ball, converges pointwise to f, then f, that limiting function, is in subspace X itself, and that limiting function f is in the closed unit ball. So this is the hypotheses that we're working under. The claim of the lemma then is, if a sequence f sub n in X is Cauchy and converges pointwise to f, then f is in X and f sub n converges to f with respect to the norm. So there's two kinds of convergence under discussion here, pointwise convergence and convergence with respect to the norm. Now the pointwise convergence, that's regular old convergence dealt with in Calculus 2, because the outputs of these functions are, say, real numbers, elements of the field. So we get outputs from the functions that form sequences when we fix an element of the set, and that's what you do when you talk about pointwise convergence. So the regular old pointwise convergence is simply the kind of convergence you deal with for sequences of real numbers in Calculus 2, or maybe sequences of complex numbers if that's the field. Now, convergence with respect to the norm, well, that's what we've been dealing with. It's usual, this sequence converges to that limit with respect to the norm. Oftentimes, and this will hold in the near future as well, the norm has been the sup norm. Not necessarily, but if it's a sup norm, then we had some sort of uniformity, uniform convergence or something, as we commented previously. So to prove this, let's look at the proof. To prove this, we need to start with a sequence f sub n in X that's Cauchy and converges pointwise to f. So take f sub n to be a Cauchy sequence in X which converges pointwise to f, let epsilon be greater than 0. Since we have a Cauchy sequence, Cauchy in the sense of the norm, choose capital N, a natural number, such that for lowercase n and m sufficiently large, at least as big as capital N, we have the norm of f sub n minus f sub m less than or equal to epsilon. Usual definition of Cauchy, did intentionally put an or equals to there, and if that bothers you, make it a strict inequality. If this is less than epsilon, then this is certainly less than or equal to epsilon. But we're going to look at the closed ball of radius epsilon here shortly, so that's why the inequality is there. Now, B bar of 1, closed unit ball, is closed under pointwise limits in the sense defined up here. So by scaling a vector in the closed unit ball to the vector epsilon f divided by the norm of f, we get a vector in the closed ball of radius epsilon. Now, what that means then is we've taken vector f, we've normalized it, divided it by its length. So f divided by the norm of f is simply a unit vector. And then we've multiplied that by epsilon to produce a vector of magnitude epsilon. And if you like, it's parallel to f itself, thinking geometrically. But any vector f in closed unit ball can be scaled to a vector in the closed ball of radius epsilon. So we've got closed under pointwise limits, this stuff about Cauchy sequences. For the closed unit ball, we can scale everything. And also we get closed under pointwise limits for a ball, closed ball of radius epsilon as well, and center 0. For a given n sub 0 greater than or equal to capital N, consider the sequence f sub n minus f sub n sub 0. So we're fixing the n sub 0 here at this stage, but n sub 0 and n sub 0 is chosen here, n is chosen here. They're both greater than or equal to capital N. So this holds. We get the norm of f sub n minus f sub, well, n sub 0 to be less than or equal to epsilon. That is, we get the terms f sub n minus f sub n sub 0 to lie within epsilon of 0. That is, they lie in the closed ball of center of 0 and radius epsilon. So, by the way, this sequence is also Cauchy. Right? Remember, we've fixed this, but we're getting a Cauchy sequence out of this. We get all these terms to lie inside a ball with center 0 and radius epsilon. This converges pointwise to f minus f sub n sub 0. Well, remember, f sub n converges to f pointwise, f sub n converges pointwise to f. So, of course, this sequence converges pointwise to this limit. So we have a Cauchy sequence that converges pointwise to f. We can conclude that f lies in the appropriate subspace, and the limit function, sorry, I shouldn't say f, I should say the limit function, lies in the closed ball of radius 1. Here, the limit function is the f minus f sub n sub 0. So the hypotheses, having Cauchy sequence that converges pointwise to this thing, says this thing is an x. Hypotheses, this thing is in the closed ball. We scale things so that we can get this limiting function in the closed ball of radius epsilon instead of the closed ball of radius 1. We commented about the closed under pointwise limit stuff for that particular closed ball. So just a matter of scaling to get that. We're trying to show that the function f is an x, and the sequence f sub n converges to f with respect to the norm. Okay, x is a subspace, closed under linear combinations, and we've seen that f minus f sub n sub 0 is in that subspace. F sub n sub 0 is also in x. I mean, we chose the original sequence to be a sequence in capital X. So f sub n sub 0 was in capital X as well. So add that to this term of x, and of course the f sub n sub 0's cancel out. We get f is in x, as claimed. F is an element of x. And the norm of f minus f sub n sub 0 is less than or equal to epsilon based on this fact here. F minus f sub n sub 0 is an element of the closed ball of center 0 and radius epsilon. So this little part gives us that norm. The n sub 0 we fixed up here was arbitrary, an arbitrary n sub 0 greater than n. So what we've shown is for all epsilon greater than 0, there exists a capital N, such that if n sub 0 is greater than or equal to capital N, then the norm of f minus f sub n sub 0 is less than epsilon. That's the very definition of sequence f sub n converges to f with respect to the norm, right? We're measuring distances there with respect to the norm. Back to the notes. All right, the following two quote-unquote theorems are really just examples of complete normed linear spaces. Complete normed linear spaces were called Banach spaces, so these are examples of Banach spaces. Theorem 214 says the space of all bounded functions from set S to field F, taking field F to be reals or the complexes, denoted B of S, is complete with respect to the suit norm. Oftentimes we'll be using suit norms. The space of all bounded functions from set S to field F is complete with respect to suit norms. So that means we need to show any Cauchy sequence in this B of S normed space, normed linear space, converges. That's how we'd show completeness. So let F sub n be a Cauchy sequence in this collection B of S, bounded functions defined on set S. For any point, I want to use that point-wise stuff we were just talking about in the previous lemma. For any point S, lowercase s, in set S, f sub m of S minus f sub n of S is less than or equal to the sup over all S, f sub m of S minus f sub n of S. We picked a particular S value versus the sup over all S values. Of course, the sup is greater than or equal to a particular value. And we choose to look at the sup because that's how the sup norm is defined. So the sup norm of f sub m minus f sub n is this quantity by definition of sup norm. So the sequence f sub n of S is Cauchy in F, in the field. So what we've shown then is for given S, the absolute value of the difference, absolute value if the field is the reals, say modulus if it's a complex number. Some folks call modulus absolute value as well. But we've got numbers in the field, their absolute value of the difference, has been made less than the norm of f sub m minus f sub n. How does that give you Cauchy? Well, the sequence f sub n was Cauchy under the sup norm. So for all epsilon greater than 0, we can make this small. Well, if you can make this small, this is going to be even smaller by the inequality. So this will be a Cauchy sequence as well for a given S. Hey, these fields are complete. Reals and the complex numbers are complete. Cauchy sequences of real numbers and Cauchy sequences of complex numbers converge. So this sequence f sub n of S for a fixed element of set capital S, namely lowercase s, this converges to some point in the field. Denote that limit value as f of S. In that way, f is the pointwise limit of f sub n on set F. On set S. This we defined by taking pointwise limits. They existed because Cauchy sequences converge here in the reals or the complex numbers in the field that we're talking about. So that's where F comes from. We simply took it to be the pointwise limit of the F sub n's. We're trying to show convergence with respect to the sup norm. Well, that's a pretty good candidate. This F here is a pretty good candidate for the limit under the sup norm also. It is the pointwise limit. If f sub n is less than or equal to 1 in norm for all n, that is if we're taking f sub n to be in the closed ball of radius 1, then for any s in the set, we have f sub n of S is less than or equal to the norm of F, kind of is what we described up here. And that norm we're taking to be less than or equal to 1. So if we look at the absolute value of f of S, some particular S value, that is the way we defined f of S. It's the limit as n approaches infinity of f sub n of S. Right? We knew convergence up here of this sequence, and its limit is what we're denoting as f of S. So definition of f of S. The absolute value of a limit is the limit of the absolute values. That's continuity of absolute value, I suppose, from maybe from calculus, certainly from senior level analysis. And each of the f sub n of s's we just showed was less than or equal to 1. So we're getting less than or equal to 1 here, transitioning from f sub n of s's to the limit values, the f of s's. But the absolute value of the f of s's are all bounded by 1. So were we to take a supremum over all s values, we get the norm of f as less than or equal to 1 as well. In other words, f is in the closed ball of radius 1. So the lemma we just stated, said, if you have this Cauchy sequence that converges pointwise, and we just showed that's exactly what we have, then we have that sequence converging with respect to the norm. And here the norm is a subnorm. So what this really gives us is an example of a Banach space. Returning to the notes, looking at this a little bit more, space of all bounded functions from a set S to a field F, the reals or the complex, is complete. So we've got then a complete normed linear space. These are examples of Banach spaces. Similar idea, Theorem 215, let X and Y be normed linear spaces. Suppose Y is complete. Then the space of all bounded linear operators from X to Y, we had denoted this in the past, so B of X comma Y is complete. Well, really, the proof is basically the same as what we just did. We'd take ourselves a Cauchy sequence of bounded linear operators from X to Y, and we'd look for a candidate limit. And we do something pointwise. As it says, we'd use pointwise convergence combined with the completeness of Y. And that's what we did up here. We used pointwise convergence along with the completeness of the output. The output was real numbers or complex numbers, and those are complete fields as well. So the proof of this is actually quite similar. We'd find a pointwise limit and use that as the candidate limit of the Cauchy sequence, and then establish that, in fact, the Cauchy sequence does converge. It's practically the same as what we did in Theorem 2.14 by appealing to the lemma at the top. So, by the way, this gives us another example of a Banach space. Speaking of Banach spaces, a subspace Y of a Banach space X is itself a Banach space if and only if that Y is closed. So let's look at a proof of that. So this makes sub-Banach spaces really easy to find. You just have to determine if they're closed. So subspace Y of a Banach space X is Y itself a Banach space if and only if Y is closed. I like this because the proof's quick. Suppose Y is closed. All right, we want to show it's a Banach space, so we want to show Cauchy sequences converge. Let Y sub n be a Cauchy sequence in subspace Y. Then Y sub n is also a Cauchy sequence in X. I mean, Y is a subset of X. So the Cauchy property carries over to the subset, or from the subset to the larger set. You measure distances, the norm's the same on both X and Y. So Cauchiness in Y implies Cauchiness in X. X is a Banach space. All right, then, so Cauchy sequence in X converges. Well, we got ourselves a Cauchy sequence in X, so Y sub n converges to something in capital X. But Y itself is closed. Closed sets contain their limit points. To paraphrase what Theorem 2.2.a part 3 stated, a closed set contains its limit points. And this X is a limit of a sequence from set Y. So this X is a limit point of set Y. And since Y is closed, it has to contain that X. X is an element of Y. And so we've got sequence Y sub n converging in Y. That is, Y is a Banach space. We knew the limit was out there somewhere. We needed that somewhere to be included in set Y in order to draw the conclusion of convergence in Y. And it is, and the closure gives that. So if closed, then Banach space, we want to look at the converse of that, actually look at the contrapositive of the converse. Suppose X is not closed. If X is not closed, suppose Y is not closed. We want to show Y is not a Banach space. Well, if Y is not closed, then there's some X, a limit point of Y, X in Y closure, where X is not in Y itself. Y closure includes all the limit points of X. So I can state it in terms of limit points if you like. But anyhow, there's an X in Y closure that's not in Y itself. So choose a sequence, Y sub n, in Y, that converges to X. You can do that because Y closure, any element of Y closure, is the limit of some sequence of points in Y that we stated in Theorem 2.2 Part A also. So we've got ourselves a Cauchy sequence. Since it converges, here I'm having a conversation in big space X, which is a nice space. Cauchy sequences converge in X for sure, because it's a Banach space by hypothesis. So Y sub n is a Cauchy sequence, but Y sub n does not converge in Y. It converges in X. It converges to this point. Converges to this point here, this little X value. But this little X value is not in Y itself. So it's very context dependent. This sequence is Cauchy, converges in capital X, but it doesn't converge in Y. Think of Cauchy sequences as wanting to converge. It would converge, but in space Y, it looks like there's a little hole in that space at point X. And that's the reason it doesn't converge. It wants to. So just between you and me, think of Cauchy sequences wanting to converge. They will if you've got a complete space. They might not if you got a space that's got holes in it that is an incomplete space. So here's a Cauchy sequence in Y that does not converge in Y. All right, then Y is not complete. If it was complete, Cauchy sequences would converge. And another example of a Banach space. Take the interval, closed and bounded interval from A to B. We know the bounded functions on A to B form a Banach space, Theorem 2.14. As we stated, bounded functions from set S to a field. We're actually taking set S to be a closed and bounded interval and taking the functions to be real valued as well. So we're good on that. So this is a Banach space. Bounded functions on the interval A to B is a Banach space under the suit norm. Consider continuous functions on the interval AB, C of AB, that is the linear space of all continuous functions on AB. A sequence, F sub n, of continuous functions that's convergent with respect to the suit norm is, in fact, uniformly convergent. Under the suit norm, convergence is equivalent to uniform convergence in this setting. So the limit of F sub n is itself continuous. Need to dig into your knowledge of analysis 1. A pointwise limit of continuous functions may not be continuous, but a uniform limit of continuous functions is continuous. So the fact that the suit norm implies uniform convergence and uniform convergence implies limit of continuous functions is continuous tells you this sequence of functions converges to a limit function, which is also continuous. And so that limit function is contained in C of AB. That is a Cauchy sequence of continuous functions with respect to the suit norm converges to a continuous function. So Cauchy sequences converge in this normed linear space. Then that's another example of a Banach space, another Banach space under the suit norm.